Hello friends, today I am here with my lesson number 6, Fermi Energy. Last lecture my was on Hall effect. Lecture number 6, we have discussed Hall effect in detail. So proceeding start. Okay, just a second. Okay. Okay, let's see the concentration of free electrons in the covalent band. In this, the energy possessed by the free electrons in the covalent band will be in the range of e base c to plus infinity. That means I'm saying that whatever electrons is present in the conduction band will always go towards plus infinity, towards infinity. So here in this diagram you see approximation energy band diagram where you can see the electrons that are present in the upper section, not in the lower section, because positive infinity is somewhat it goes to the upward side. And when you see the same figure in the exact energy band diagram, you can see this where energy is in electron volt. The same is represented in the other way. Here you can see the electron again present in the covalent band. So this is a concentration of free electron in the covalent band. It goes towards plus infinity. Okay. Now the concentration of electron in the covalent band, it's always given by this formula. This or this formula, both are the very same formula. Here the only is representation of E. Here you can see E is either represented in this way or in this way. In either way you can write the same formula. You just need to be aware of both the things. The main task of yours is to remember the formula that is written within those blocks, brackets. Not exactly bracket, it's a block, grayish block. Okay, so in the above formula, K represents your Boltzmann constant, N base C is a material constant, and E base F is your Fermi energy in electron volt. And again this formula, Nc is represented with this formula. You have to remember the formula. Okay, so in the above formula where H is your Planck's constant, and you have to remember the value of Planck's constant and unit, of course. M base n is your effective mass of electron. Here you can see M base n is the effective mass of electron. Let's see, for example, we consider silicon. For silicon, Mn divided by M is always 1.08. So if you do the cross multiplication and all, you will get this M base to 1.08 M. Now you know simple M is the rest mass of the electron, and you know rest mass of electron is given by 9.1 into 10 to power minus 31, and your M base N is 9.8 into 10 to power 31. It's just calculated. In this cross multiplication we just put the 9.1 into 10 to power 31 and we get 9.82 into 10 to power 31 minus 31 kg. So what conclusion is made out of this is your effective mass of electron is greater than the rest mass of electron. On calculation we have got this. Okay, so this is the conclusion we got. So we proceed the concentration of holes in valence band. In the previous case it was going towards plus infinity. Now in this, let's see, the energy possessed by the hole in the valence band will be the range of minus infinity to EV. If you refer your previous diagram, just see that I'll show you here. If it goes from minus infinity to the e base e, that means whatever are present will be present in the lower section, not in the upper section this time. I haven't repeated this diagram again, you can prefer your previous diagram. So everything is same. Instead of electron, we're talking about holes. So in the lower section, the holes will be present, and the concentration of holes again is given by this or this formula. Again, the difference is only in the E representation. Now here, instead of n base c, the material constant is n base v. So n base v is given by the same formula. Everything is same over here. Now here, instead of m base n, we have m base p, which is the effective mass of holes. Okay, and again let's consider silicon. M base p divided by m is 0.56. If you do cross multiplication, the rest mass of electron, you get 5.09. so it's clearly very less, right? So effective mass of hole is less than rest mass of holes. So we have made two conclusions out of that. Your work is to remember both this conclusion, because in PSU exam they ask direct questions, and germanium and the silicon is a very famous material, so the question is basically raised on germanium or silicon, or they can ask about gallium arsenide. So for both germanium or silicon, your m base n is greater than m base p, but for gallium arsenide it's opposite. So you just have to remember the difference. Don't try to just mug up, just go through it. If you go through it once, it will be like, whenever you see this question, it will be automatically flashed in your mind and you'll get your answer. Okay, moving to next. Let's derive an equation for Ni. Derivation is not important if you're preparing for objective exams, but of course you have to remember the formula, because there are many numericals coming in EDC. So remember every important formula I have mentioned in this gray boxes. So try to remember everything. And if you're preparing for any IES kind of exam, then of course derivation is important. So for that case, you can go through. It's very simple. See here, electron n is equal to this formula. This I've already shown in previous slide, and very same for holes also. If you multiply both the equations, you get n base I. So n into p is equal to n base I square, and that is a multiplication of 1 and 2. We get this. Now why I have written minus e base g is EF is cancelled. So when it's like EC minus EV, this is just an energy gap. If you do the mathematics, it's not possible for me to show every step. So if you do your step one by one, automatically you'll come to this step. Okay. So now n base c and n base v is equal to a naught t to the power 3. So I have replaced 4 into 3, and on substitution we get this. Or from the left hand side, if I have removing the square thing, here the root is coming over a naught, and t to the power 3 becomes t to the power 3 by 2, and everything remains same. So remember this formula, it's important. Okay, so Fermi energy. What is Fermi energy? Fermi energy is represented by E base F. Of course, I have taken this notation many times in the previous slides, lectures and everywhere, so I think you are very much aware now about this. Okay, so it's measured in electron volt always. It is defined as a maximum energy possessed by an electron at 0 Kelvin. Okay, your Fermi energy is also defined in the other way, and other way is like, it is defined as a maximum kinetic energy possessed by an electron at 0 Kelvin. Okay, Fermi energy is maximum kinetic energy, almost equal. So E Fermi energy is equal to half mv max square. So maximum velocity of electron is given by this formula. It's nothing, just you're calculating v max out of this. Or the third way of defining same Fermi energy is defined as the energy possessed by the fastest moving electron at 0 Kelvin. So there are three ways your question can be raised, like if you define Fermi energy, options can be any one out of these three. So you should be prepared in all three ways. So I hope it's clear to you. So next is Fermi Dirac function. It's represented with the notation F bracket E. The bracket is capital E. It's sometimes also known as Fermi Dirac probability function. See this round figure. In this round figure, N is electron, P is holes. If N is represented with this F bracket E, so P is of course 1 minus P is holes. If some quantity is electrons, the rest of this is of course holes. So for a metal or semiconductor, F, your Fermi Dirac function is given by this formula. Okay, in this you can see that your capital E is the energy possessed, your capital E is energy possessed by an electron in electron volt. This is capital E. And your Fermi Dirac function, this indicates the probability of electron existing in a semiconductor or metal as a function of energy. Okay, next, now let's see the case when temperature is 0 Kelvin. What happens? So when temperature is 0 Kelvin, we have three cases: when E is here greater than Fermi energy, when E is here less than, and when E is equal to Fermi energy. So when E is greater than Fermi energy, what happens? Greater means something, when you do it step by step, you will automatically get. E means if E is greater, something subtracted from the lower term, you'll get something in positive. So you're just replacing this in the previous formula. Okay, so we're getting this some plus. Plus means it will go to the e to the power infinity and we'll get 0. So probability will be 0. So what probability means? Probability is 0 and it indicates that when temperature is 0 Kelvin, number of electrons available with energy greater than Fermi energy are almost 0. No electrons will be having that energy. Okay, second, when E is less than Fermi energy, again when E is less, something will be negative, that is minus infinity, and it will be 1 or 100%. In the terms of percentage, it's 100. So this means probability is 1 and it indicates that when temperature is 0 Kelvin, electrons are available with energy less than Fermi energy. There are electrons. The probability is 100%. Okay. Third, when it's equal, your Fermi Dirac will be in the intermediate form. 0 by 0 gives you intermediate form. So remember the cases. Next is when your temperature is greater than 0 Kelvin, of course. So in this, when E is equal to EF, in this case it will be 1 by 2. 1 by 2, that means if half means probability becomes 50% or 0.5, so probability will be of course 50%. That means probability is 50% and it indicates that when temperature is 0 Kelvin, greater than 0 Kelvin, electrons with energy is equal to Fermi energy may or may not be existing. It may exist or it may not exist. 50% means this. So in metals, the probability of electrons existing at temperature greater than 0 Kelvin is 50%, and in a semiconductor the probability of electrons existing is F bracket E, and the whole is given by 1 minus F bracket E. Okay, so Fermi level in intrinsic semiconductor. Intrinsic means no doping. No doping means N is equal to P. These things I've already I think I've told you in my previous videos. So when it's intrinsic, N is always equal to P because there's no doping. So simply we are just substituting N is equal to this thing, and P is equal to this formula. So we're equating both the things. We're calculating NC by NV on taking NC divided by NV. Right hand side terms looks like this. When you take log on both the sides and further you calculate, you'll get this thing, and finally you'll reach to this formula. It's a very important formula, and numericals are very famous from this topic, so be thorough with this formulas. So EF is equal to this. Okay, so in intrinsic semiconductor, your Fermi energy depends only and only on temperature. We play with temperature and see the cases. Okay, so first case is here. Let's assume that M base N is equal to M base P. Now every time I'm not going to say what is M base N, what is M base P, because I've already told you it's a rest mass, and it's a rest mass of hole and electrons both. So when you assume both are equal, then of course N base C is equal to N base V, and when you take log it will become 0. So finally your Fermi energy will be this thing. This indicates that the Fermi level is exactly at the center of energy gap. You see in this figure, it's almost at the center. And when you in the figure other figure, it's telling about the concentration of electron in holes and the Fermi level existence. You can this red thing indicates the presence of electrons in holes, which are almost equal. Okay, so the next is when temperature is 0 Kelvin. Again here the same thing, your Fermi energy will be exactly at the center. So for case 1 and case 2, this both figure are the same. Case 2 also it remain the same. So the question which can be raised here, in intrinsic semiconductor, under what conditions your Fermi energy is existing exactly at the center? Now, there are 3 conditions if we go through it properly, and the 3 conditions are when your Mn is equal to Mp, where Nc is equal to Nv, and when your temperature is 0 Kelvin. If all the 3 conditions exist, then your Fermi energy lies exactly at the center. Third case is when your temperature is 300 Kelvin. Now by default it's Mn is equal to Mp, right? If Mn is greater than Mp, then Nv will be slightly greater than Nv. Now what happens is, in intrinsic semiconductor at room temperature, that is 300 Kelvin, your Fermi energy will be passing through the center of Eg, and it is slightly above the center of Eg. But at the room temperature, because of thermal energy, number of covalent bonds will be broken and equal number of electrons and holes are created, and there will be a conductivity in the semiconductor, of course. So in the figure you can see the electron concentration and the hole concentration are almost same, or you can say it's same. Okay, so now the fourth condition comes here. It's the position of EF at different temperature. We're just telling you what happens when the temperature is 0 and goes on and increases. So you see, as temperature increases, initially you see the red color. Red color shows when temperature is 0 Kelvin, then green color comes, then blue color comes, and it goes on the opposite. Green is your 300, then 330, then above 330. So as temperature is increasing, more covalent bonds are breaking up and more electron and hole concentration, and also of course conductivity increases with temperature. This I'm telling you from the very first lecture, that conductivity always increases with temperature. Similarly, let's see for the n-type semiconductor Fermi level. If it's n, the electrons are dominating part, so n will almost be equal to n base d. Replacing n is equal to with this thing, n is equal to nd, nc by nd is again taking log. Everything is similar to our previous slides, taking log, and again you're coming with this formula, bracket block formula. In n-type semiconductor, Fermi energy depends on temperature as well as on n base d. Now see, when temperature is 0 Kelvin, what happens? When temperature is 0 Kelvin, your Fermi energy will be equal to covalent band energy. Okay, so see here the figure. Here the Fermi energy almost coincides with the edge of conduction band. Okay, and here it's a Fermi level position. In this figure is showing the Fermi level position and electron and hole concentration. It's shown by green color, light green color. So I have tried to provide you the diagram so that you can visualize everything, see it properly, and it go and stuck in your mind. So at 0 Kelvin, electron and hole concentration are 0. So of course the conductivity is also 0. When both are 0, conductivity is 0, and hence semiconductor at 0 degree Kelvin, it acts as an insulator. Okay, and again if I'm talking about case number 2, 300 Kelvin, EF is equal to EC minus KT. This is a formula, and where temperature is your 300 Kelvin. Okay, you know EC minus ED is always 0.01 for germanium and 0.05 for silicon, and EC minus EF is 0.3 electron volt or greater than this, of course, in this value. Okay. In n-type semiconductor, when temperature is 300 Kelvin, your Fermi energy exists just below the donor energy level. See the first figure. It's almost, the green is just below the, just a second, below the donor energy level. Fine. Red is your donor energy level and E is base F is here. Okay. In n-type semiconductor, what happens? Semiconductor, as temperature increases from 0 to 300 Kelvin, at some intermediate temperature, there will be some intermediate temperature, the Fermi level will be coinciding with the donor energy level. Okay, and in terms of the concentration, I have tried to provide you the diagram. You see the electron concentration is greater and the hole concentration is less. Or the other way, I have tried to show you that simply in the single diagram you see the electron concentration is high and the hole concentration. In any way you can understand, either first, second or the third diagram. Every figure indicates the same. Case 3, effect of temperature, that is temperature when temperature is greater than 300 Kelvin. Okay. When temperature is greater than 300 Kelvin, as temperature increases, you see, then N base C also increases. Now let's suppose N base C is equal greater than N base C. EC minus EF is greater than 0 or EC is greater than EF. In n-type semiconductor, whenever temperature goes above 300 Kelvin, your Fermi energy moves away from conduction band. You can say in either way, either it moves away from conduction band or it moves toward the center of energy gap, any of the way. So when that happens, the conductivity decreases with temperature. In n-type semiconductor also the position of Fermi energy at different temperature is different, and you can see here the figure, when it's 0 Kelvin it's almost coinciding with the conduction band. When the temperature is 300 Kelvin it's shown with the orange, and with the blue shows 300 to 400, so it's coming down, moving away from the conduction band. Okay, at Curie temperature, T base C indicates Curie temperature, the Fermi energy level will be existing exactly at the center. I told you that some intermediate temperature it will be coinciding with your Fermi energy, so this is the at Curie temperature it happens. So what happens? Fermi energy depends on doping. Okay, Fermi energy also depends on doping. As you do doping, if you do doping, then your n base d also increases. Now let's say here n base d is greater than n base c only when doping concentrations are high. In this case, EC will be less than E base F. So in this case, what happens when n base d increases? Fermi energy moves towards conduction band, or in the other way, it moves away from the center of energy gap. So conductivity increases with doping. It is a vice versa of the previous. Okay, so now case 4th is shifting in the position of Fermi energy due to doping. How doping makes a difference in the shifting position. Shift is always given by this formula. Okay, shift is KT. Shift is this. Everything is mathematical. You have to remember it. Okay, so this blue, the arrow I have tried to show you. This is N E base F N and E base Fi. So this width is your shift. This shift happens, this thing, shift in the position of Fermi energy due to doping, shift in the Fermi, or you can say that shift in the position with respect to the Fermi energy of intrinsic semiconductor, or you can say that shift in the position of Fermi energy with respect to the energy gap. Any of the way you can say that. Fermi level in p-type semiconductor. Whatever I have, you have remember in n-type semiconductors is almost the same, The only thing is instead of electron now just have holes, and in the place of n it's p. Everything is same, taking log and then calculating, you get this formula. In p-type again it depends on temperature and n base d. Now previously it was n base c. Again, when temperature is 0 Kelvin, everything is same. Figure says that your electron or hole concentration at 0, electron and hole concentration on 0, so there is no conductivity. And in p-type semiconductor at 0 we will be again working as an insulator. When temperature is 300 Kelvin, again it's a formula, and the Fermi energy will be exactly below the donor energy level. So when your temperature increases from 0 to 300 Kelvin, at some point the Fermi energy will be coinciding with the donor energy level. So this is again the same figure. In either way you can see, either in the first EA, except this is a accepted energy and this is your accepted energy here. So in the terms of both are almost same, electron and hole concentration. Third is telling about Okay, as temperature increases above 300 Kelvin, your Fermi energy moves away from the valence band, you can see, and or you can say the Fermi energy moves towards the center of Eg. Okay, I just want to tell you that if you go through any, either you go through N or either you go through P, if one is very much clear to you, the other is vice versa. So be thorough with one. Don't try to remember everything. Try to understand the things. So okay, so if you remember the figures in your brain, in your mind, so whenever you see the figure, it will automatically click you. So here you can see the Fermi energy. So I have tried to show you with 3 different colors when temperature is 0 and when how it is different when 300, 360 and goes on. Okay, it also depends on doping in the same way for electron. As doping increases, your N base A also increases, and everything is same. Everything is same in this. So there's no point of explaining you again the same thing. I hope you people are very much mature. If you have any doubts, of course you can write down in your comment box and ask me. Otherwise everything is same. There's no use of telling you the same things again. Go through my slides carefully. Be thorough with the figures, notations and of course formulas. So again, depends on doping. Shift is again here the only difference in the shift, we have a negative side, negative sign of course. So remember the formula. Okay, so guys, thanks for watching my video, and here we are over with the basics of ETC part 1, and I'm planning to upload my part 2 very soon. That's on semiconductor diodes. We will be talking about diodes, Zener diode, tunnel diode, contact diode, semiconductor diode, many diodes, whatever is there in the ETC and comes in the competitive examinations. So be in touch for upcoming videos, and please don't forget to subscribe and like, and of course comment down, and thank you so much for watching. Stay in touch. Bye bye.